Good afternoon. Thank you very much for coming. We have great pleasure today to host Tony Picker from Manchester University. Tony is world expert in the area of recombination in semiconductor and defect in solids. He has very rich career that started in the late 60s. He was involved with the first commercialized of the first visible LED, the first UK solar cells. He also founded two startup companies and developed the Laplace DLTS. In the last year, his focus shift or maybe back to silicon, and he has a very nice work on nano precipitates and oxygen-related recombination. So please join me and welcome Tony.
Well, thank you very much, Ziv. Well, as Ziv has said, I'm going to talk today about some of the work that we've been doing on recombination in solar silicon, and I'm going to start off by, first of all, defining solar silicon, if that's possible, or at least defining the sorts of solar silicon that I'm going to talk about and trying to highlight the differences between them. I'm then going to put in a bit of tutorial material on recombination, quite short, but then you'll know the techniques we're using and what limitations they have. And then I'm going to move over to talking about specific material types that are used for various methodologies in solar cell production, obviously Czochralski, and then continuous Czochralski. Cast silicon, of course, and this issue that they've mentioned, a new type of recombination center which we think is potentially very important, that we've called nano precipitates. Then I'm going to talk about Kerfless silicon, a particular type of Kerfless silicon, and then I'm going to finish off by talking about hydrogen passivation. So the concept is that electronic grade, float zone and Czochralski silicon, which is nearly perfect, very, very few dislocations, very, very few defects, and almost no detectable electronically active metals in it. But it's generally regarded as too expensive for solar, and so people have worked very hard to try and produce material more cheaply, which is of good quality from a recombination point of view and from a structural point of view as well. And there are really two stages to that. That's producing the polysilicon material, which is used as the feedstock for the second process, which is growing the crystals. In producing polysilicon, electronic grade material, it's normal to use something that's like the original Siemens process. So this is taking, if we look at the little pathway there, I've lost we look at the pathway here, that we reduce the quartz with carbon, produce elemental silicon, and then that has a lot of impurities in it. We convert it to trichlorosilane or to silane, and then purify that by fractional distillation and other techniques, and then produce polysilicon from that. So this is the Siemens process, and down in the corner here I've got a little graphic which shows you the old-fashioned Siemens process, depositing the trichlorosilane on heated rods and then breaking them up and using that as polysilicon. So this is very energy hungry, so this is quite an expensive process. So the first stage that's happened, and it's also happened for electronic grade material, is to use a more energy efficient technique. Instead of a batch process like this, to use a continuous process using a fluidized bed, and this produces nice granules of polysilicon. So this can be made, and you don't necessarily sacrifice much purity in doing that. But more radically, what people have done is to try and miss out the Siemens process, this energy-hungry process, and to try and use upgraded metallurgical silicon, so to essentially to getter this at the poly stage by using aluminium, all sorts of different techniques to try and get some polysilicon which is much cheaper, and it contains very high quantities of potentially damaging elements, metals in particular and transition metals specifically, and that has to be dealt with somehow in the following processes. We then need to convert the poly into single or multicrystalline material, and of course in electronic grade the traditional way of doing that is Czochralski or float zone growth, and both of these use the segregation between the melt and the solid to purify. And this is really the tremendous advantage of these processes, that at that growth stage you reject the impurities by a factor of about 10 to the 5. And so Czochralski and float zone are generally very, very pure material. But it's expensive, and so again you're looking for lower cost materials, cheaper growth processes. And the other thing is to reduce or eliminate the cutting losses as a cost factor. And this is where the Kerfless silicon, you don't actually have to cut this. You actually produce it, grow it, either as ribbons or as slices, and you miss out this wasteful process where you throw away quite a lot of the silicon as you're going to thinner slices. You eliminate that. But often these approaches, you've got a reduction in the cell efficiency because of a decreased minority carrier lifetime, and that's the parameter that we measure in general in my lab to try and get a measure of how good the material is, what the minority carrier lifetime is. But I think a very important thing, and this has become more and more significant as the years have gone by, is that reducing the cost of the material is not necessarily beneficial. You have to look very carefully at what price you're paying for that in terms of reduction in efficiency. And the calculation has changed over the years, that because the price of silicon has gone down, other things have become much more significant, the installation costs in particular. And if you're reducing the efficiency, you need more area, so you're increasing the installation costs. So the economics is quite complicated, and it depends on which country you're in. It costs a lot more to install cells in Germany and the UK and Europe than it does in many developing countries. So important to look at the right economics that you're using. And I think increasingly the issue is that efficiency is everything. That if you can get a much more efficient cell for not too much more money, then you're going to win out in the cost per kilowatt hour delivered. And so the focus is increasingly on improving production, the efficiency of production cells. So float zone and Czochralski, you have this segregation coefficient that I've mentioned, which gets rid of most of the transition metals. And in electronic grade material, and indeed in solar grade Czochralski material, the transition metals are usually undetectable. And if they are there, it's due not to the growth, it's due to something in the cutting process, the cleaning process, or something like this. So typically have less than 10 to 16 carbon. In Czochralski, you incorporate oxygen from the crucible, so you're looking at 10 to the 17, 10 to the 18 oxygen. And this is significant in p-type because of this annoying boron-oxygen reaction, which reduces the efficiency by about 10% during the life of the cell. Very few extended defects. So the other major production method of producing silicon slices is by casting. This is by far the most common. It's many variants on the way that this is done. But essentially you get contamination from the crucible, diffusing in from the base and from the sides. You don't have the segregation of the transition metals to improve your material all the way through the ingot. So the transition metals are rejected at the bottom, but as you get towards the top, the concentration increases, particularly in the top layers. People have tried to seed the growth so it becomes more crystalline. The results of that are, in large seeds, are not particularly successful. You tend to get clusters of dislocations produced towards the top of the ingot, and these are decorated, so you get many extended defects, and the efficiency is not too good. So it's getting rid of these that's the trick in growth, and a lot of a tremendous amount of proprietary information as to how you actually do this. The two techniques that I've got here are not as widely used. They're still really at the experimental stage, although both have been used in various methods for a long time, but they're still not, as far as I know, not in production for solar. So continuous Czochralski is not really continuous. You just can't continue to grow a large ingot through the roof of the building and up into the sky. It just becomes too heavy and you can't support it. And but what you can do is that you can feed in a polycrystalline material as the material grows, and reuse the crucible, reseed, and things like this. So that's a very interesting technique, and I think has a lot of potential. Kerfless silicon, well, ribbon silicon, people have used this for decades and decades. That's not what I'm going to talk about. What I'm going to talk about is a development that we've looked at, which uses the growth on porous silicon, which is the old Canon Eltran method for producing silicon on insulator. And a startup company has developed that into what looks like a commercially viable technique. And essentially what you're doing in that is to eliminate these stages here. This little animation from the company shows you Crystal Solar, shows you what they're missing out. So you take your material, you convert it to the in their case trichlorosilane, you grow on porous silicon, and then by arranging this in such a way you can cleave off the slice, and if you get everything right you get very high yields and you go immediately to producing the cell. And if you can, certainly if they can do this economically, then it works out as a rather wonderful way, because you no longer have the waste from cutting your cells. You have potentially the very high purity of epitaxial material. Looks wonderful, but time will tell. So what we're trying to do is to look at the dominant recombination paths in these various types of material, see what is degrading the lifetime, degrading the efficiency, and the techniques that we're using it are lifetime measurements and variants of deep level transient spectroscopy. So this is actually looking at the concentration of specific defects in a Schottky barrier or a p-n junction. Most of the work we've done is on just the starting material, but sometimes we put in process steps, annealing and gettering as a simulation of what will happen to it during the production cycle. And sometimes we use part processed silicon and cells. Cast silicon, this works very well with almost everything but cast silicon. Cast silicon is a nightmare because it has so many different defects in it. And you have variations through the depth of the incross between the center and the edges, and over the area of the slice there are a lot of different types of recombination that are going on, So you see enormous variations in lifetime across the slice. So this is a pretty disaster slice. This is about a microsecond lifetime. It's made from upgraded metallurgical silicon, and it's from the top of the ingot where there are loads of clusters of dislocations, and there's also loads of transition metals. So everything you could imagine is wrong about this material. And measuring it and assessing it is very, very difficult. So recombination, you can generalize about this in semiconductors. What we're perhaps most interested in is Czochralski-Reed-Hall. So this is a process where we get recombination through a defect state here, which in the case of solar is usually a metal, and usually a transition metal. And the energy is dissipated by phonons, and of course it takes away from your generation of carriers in your solar cell. Surface recombination is also very important. Depends on the surface passivation techniques. Sometimes depends on what impurities you've got, so it's a sort of surface variant of this process here. Radiative recombination, not important in silicon at all as a competing mechanism, but crucial in direct bandgap materials. Auger increases as the square of the carrier concentration for band-to-band Auger, and so it's important in highly doped materials. So you have to design your cell to avoid getting Auger recombination. The mechanism is that you get recombination, the energy is taken away by a third carrier. But what you have to remember is that all these rates are additive, so that the lifetime is the sum of the reciprocals of these. So they're all significant. So here we've got a little plot of the lifetime against carrier concentration. The radiative lifetime is up here. Not significant, not impinging on the lifetime at all. Here we've got the line for band-to-band Auger. And as you can see, that increases steeply as the square of the carrier concentration. Here we have the Czochralski-Hall-Reed lifetimes. So when you're getting to around a millisecond, which is what we want to see in solar, Auger recombination starts to kick in about 3 or 4 10 to the 16. People say this about Auger recombination, but they talk only about band-to-band Auger. In reality, there are many types of trap Auger process, which in certain circumstances can be more important than the band-to-band Auger. But we will, like everybody else, neglect that for the moment. So the Czochralski-Hall-Reed recombination is obviously the thing we're going to talk about as being most significant, and it depends on the defect concentration and also on the defect properties. We measured the lifetime with a semi-lab machine, a WT2000, which you have one here, but you don't rate it very highly as a method of measuring lifetime for many good reasons. It works in a quite high excitation density regime, usually 10 to the 14 to 10 to the 16. And the process is simple. You hit it with a laser. You can choose what laser you want. We use about 903 nanometers usually. And then you pick up the changing conductivity with a microwave signal at 10 gigahertz. So it's quick and easy. You can map with that. And the resolution is about 0.5 millimeter on our machine. In the Czochralski-Reed-Hall process, we need to look at the properties of the states involved. These are a sort of schematic of trapping, so the carrier is trapped and then released. And this is significant in a number of ways, because this is the way we measure deep states, but it also perturbs the lifetime measurement. Trapping can give anomalous results in lifetime measurements, so you have to be careful about that. And the other process is generation here. So this will happen in depletion region, not significant in solar, well, not in the recombination process. But this is the recombination process. And this happens in the bulk of the material where you have both electrons and holes. The same state can do all these things. It really depends on the environment that you know, you're going to see this in the depletion region, you're going to see this in the bulk. At low excitation densities, it's the minority carrier behavior that is significant. And you can do a hand-waving approximation to the lifetime. So the lifetime is the reciprocal of what we call the capture cross-section, the thermal velocity, and the concentration of the number of states. And similarly for N-type. These will saturate at higher levels, and this is important in concentrator cells in particular. So this is the way we measure it. We have these defect states, which can be metals or they can be structural defects. We capture into this by flooding this region with carriers. I've drawn it for electrons here. And then we release the carrier. So here, with this process, we can get the capture cross-section, which we needed in the equation there and in the full equations of Shockley-Hall-Reed. And in this process, we get an activation energy, which is approximately the depth, the distance of this from the band. And this increases exponentially with temperature. And so that we can look at this over a very wide range of conditions and look at lots of different defects using this technique. So that's basically the method that we use, and this is the sort of result that we get. So in conventional DLTS, we're looking at a change of capacitance, which is measuring the charge in the depletion region, measured at 2 points in time. And this technique was invented by Dave Lang at Bell in the 1970s, and he called the separation of these 2 points that sampled it the rate window. So by changing the rate window, essentially you're changing the timing in the system, and you're looking at different time constants. So in the DLTS plot, you change the temperature, and because of that exponential term of the emission depending on temperature, then the emission rate changes, the rate window captures this, and you can look at different defects. So in an ideal case, and I've shown you an ideal case to start with, obviously, this is just irradiated N-type silicon. You get a peak. This is a vacancy oxygen defect. This is the single acceptor state of the dye vacancy, and this is the double acceptor state of the dye vacancy. So this is illustrating an important point. This is exactly the same defect. You lose an electron, you have some lattice relaxation, so its energy changes a little bit. And so you see it as two different defects. And in an ideal world, of course, you would have exactly the same peak height, which is a measure of the concentration. And this is really the wonderful thing about DLTS that separates it out from lifetime measurements, that separate it out from photoluminescence, that you can get an absolute concentration of the specific defect that you're looking at. And it has high detectivity as well, perhaps not as high as we'd like. So that's the important thing, so that from this very simple measurement, you can get all those parameters to calculate what each particular defect is contributing to the recombination. So if you're lucky and the experiment works out okay, then you can say it's this peak here which is the most significant one. This is what's killing my material. And then if you're really very lucky, you can go and you can plot this emission rate. We correct it by a t-squared factor, because of the way that the equations run, and then plot it as a reciprocal of temperature, and you get an Arrhenius plot, and you can match that up to a library, and then you can say, right, that's the dye vacancy. And if you've got two peaks like this, then you're pretty certain that that's what you've got. Nearly 100% certainty as that's what you've got. So that's the DLTS technique. But as I said, if you're lucky, you can identify from it. But in doing a DLTS technique like that, you taking this very crude filter of taking a sample at 2 points, you're throwing away most of the data that the sample is telling you. And the DLTS peak is broad. On photoluminescent, if you compare with photoluminescent, it's very broad. So you can get nothing really from the line width, nothing significant from the line width. So we worked, and us and many other people worked for many years in trying to get rid of what is really instrumental broadening. It's nothing to do with the fundamentals of broadening due to temperature or anything like that, but we worked on getting rid of the instrumental broadening. And the result of that was that we managed to find a way of doing this, which was simply using an inverse Laplace transform. The mathematics and the computation in doing that is tricky, but you can do it. And so I put here a comparison. So this is a DLTS plot, and in this there are two defects. The gold acceptor and the combination of the gold acceptor with hydrogen. And you can see it's impossible to tell that there are two defects from the conventional DLTS. But with the Laplace DLTS, absolutely no problem. It's very clear that there are two defects there. So you've got a big improvement in energy resolution in the Laplace technique. And you can do experiments. You can heat and cool this. The hydrogen bonding in this case is rather weak. So by heating it up to 120 degrees, this peak goes down, this peak goes up, and you can follow it during the measurement. So that was a long time ago. That was 20 years ago that myself and Leszek Dobroczewski developed that method. And we've reviewed it there. So the whole story is there in Physics, Journal of Applied Physics, which the review section was then included in the normal journal. So you can do lots of things with this. I've just put a couple of examples into this talk, so that this is silicon germanium with gold in it. I'm sticking to gold, and the actual energy to release the electron from the gold depends on the local environment. It's not just the way it's bonded to the lattice. But if you perturb the local environment, it's going to change that energy. And one way is, of course, for it to be there in an alloy. And in an alloy, in silicon, the germanium has 4 nearest neighbor states and 12 second nearest neighbor states. And if you have germanium there, you get a perturbation to the emission rate, and you see that in the Laplace peak. So this is with 1 germanium the nearest neighbor, 2 germaniums the nearest neighbor, and you can go on like this. And so this is just adding a bit of germanium to the silicon, 0.5%, 1%, and at the bottom 5%. And so again, absolutely quantitative. So you can work out the siting preference, where the gold prefers to sit in the ternary alloy. And so that's something which is potentially very useful in solar materials. This is a much more difficult thing to do. This experiment probably takes about a month to do, of hard work by a dedicated PhD student. So it's not something that you do every day or you do in an industrial lab or anything like that. But what you can do is to apply uniaxial stress to a sample that has a particular defect in it that you want to learn a lot about. And you apply the stress in the three principal directions, and from that you can get out the symmetry. Again, you know, an analogy with photoluminescence, you get splitting. So this is with no stress. This is with stress in the 100, 110, and 111. And you get different splitting patterns and different ratios of the splitting. And so you can look at that, and this is the double acceptor state of the silicon divacancy, which I showed you before. And looking at the three directions of splitting ratio, absolutely no doubt what the symmetry is. So it's got trigonal symmetry, and you can work out the space group. But also the magnitude of the splitting with a particular stress is very significant, because this is something that you can actually calculate and get with a fair degree of accuracy from ab initio calculations. So from this you get the symmetry, and from the calculations you can say really where it is in the lattice. So you can say, is this substitution, or is it interstitial, etc., etc. A lot of information you can get from that. So let's move on to the materials. As I've said, I'm going to deal with Czochralski and continuous Czochralski, cast, Kerfless, and then hydrogen passivation. So let's first look at a very old bit of but absolutely excellent data from what was called the Westinghouse experiment. And they threw lots of different transition metals and other things into the melt. They grew slices. They measured how much they put in the melt. They measured how much was in the slice, so they got the distribution coefficient. And then they made solar cells. And so what you see in this in this graph, which was prepared by Rahagati, who's now at Georgia Tech, is the normalized efficiency plotted against how much of the impurity was in the slice before processing. And so you have, you know, some things are very bad, some things it doesn't really care about. Now, this is very strange, because if you look at the electronic properties of these defects, they certainly don't go in this order, and there isn't an awful lot of difference between them. So this is a graph that is one of the most misinterpreted in the whole of the solar business. That people say, oh goodness, titanium, this is a real killer. Well, it is a real killer, but why? And the reason is nothing to do with the properties of the metal, but it's to do with gettering. And so that if you look at the sequence here, it is exactly the sequence that appears in the periodic table. And if you look at things like diffusivity and solubility, not surprisingly, they go exact or nearly exactly in the sequence in the periodic table. So what you're actually saying with all this tremendous work that was done is that it's much easier to get a copper than it is titanium. Sure it is. Look at the difference in diffusivity, and look at the difference in solubility and its effect on precipitation. So that's really something that's very important. And this experiment has been repeated in the last few years in polycrystalline material as well. And the results are not a million miles different, but there again, you wouldn't expect them to be very different, because what you're measuring is the gettering ability of a particular process. So if you change the process, then you may well change, of course, the order in which these occur. Well, having said that, let's look at electronic grade material. If you look at a slice that's delivered by one of the big companies, by St. Edison or something like this, and you plot the lifetime of electronic grade material, you see nothing. There is no change in lifetime across the slice, and the lifetime is very, very long. the material is virtually perfect. So what I've put here is a photograph to show how easy it is to make it imperfect. So this was just had nitride deposited on it. Before you deposited the nitride, it was uniform at about 5 microseconds or so. And of course, as soon as you touch it with tweezers, as soon as it rests on something, you get contamination. And that's what's happened to this slice. It's been badly handled, and you have localized contamination. So you see that very clearly in the lifetime map. Can you see it in DLTS? Well, the answer to that is it depends, because DLTS detectivity is a ratio of the carrier concentration. So what you can see in this 20 ohm centimeter slice, so that's about 6 times 10 to the 14 p-type, you cannot see in 1 ohm centimeter material. So we say that if you've got a commercial system, you can always see 10 to the minus 4 of the carrier concentration. Our best systems, probably about 2 times 10 to the minus 6 of the carrier concentrations. We have a project now to try and improve that by an order of magnitude. So maybe we'll improve on that. So a commercial system, you could see, yes, the red areas you could see, and because it's 20 ohm centimeter material, if it's iron, and it almost certainly is iron, it corresponds to about 10 to the 11 iron. And you could see that in just an ordinary DLTS machine that you buy from Semilab or anybody else for that matter. But you would not see it in a typical doping for solar material. And so DLTS is incredibly sensitive compared to SIMS or any chemical techniques, but it's not as sensitive as lifetime measurements by any means. Continuous Czochralski is a technique where during growth you feed in the polycrystalline material. You have to separate it from the growing ingot. You have to put baffles here. And when we were asked to look at this material, I thought it's obvious. You pull, the transition metals are rejected into the melt. They're not in the ingot. So as you keep on pulling, this melt is getting more and more contaminated, and the material will get worse because you have more transition metals in it. That's not the case at all. And in fact, the transition metals, most of them are lost from the melt by evaporation, and you see in this little schematic here that you shield the growing ingot from that because the transport of the transition metals from the melt to an ingot, many years ago people discovered that was from the vapor phase, and so they put baffles in here to stop that. And you flow inert gas, argon gas, to flush away across the top of the melt and get rid of those transition metals. So the lifetime does eventually go down. You get an increase in the number of particulate defects that you see in this material, but you can just keep on growing and growing and growing until the crucible wears out. So you save on the cost of the furnace hardware, which is quite significant. Also, you can grow much faster. You can only grow to a certain length here, and then you reseed. So this looks to be a very, very good method of growing high quality Czochralski, and the people doing it think it's going to be much cheaper than conventional Czochralski. The real drawback is that it's very difficult to do anything but a circular ingot and maintain the low dislocation densities with Czochralski. So Martin Green told me yesterday that in fact people have grown square ingots with Czochralski. but certainly the people that we know that are doing the continuous Czochralski haven't been able to do that. So you've got to cut it into pseudo squares, and again you have a lot of waste in the method. Well, cast silicon, everybody here I'm sure is very familiar with this. We've looked at a lot of cast silicon from various people, but particularly we've looked at monocasts. So this is putting seeds in the bottom and then growing from those. And it doesn't really work. You get massive dislocations in the top. And here you see, I forget exactly where, I think this was cut from about the middle of this ingot. It shows you the effect of gettering and the sort of effect that we always seem to say when you do a gettering process, that the good parts get better and the bad parts get worse. If you look now, just taking a little corner of that bad bit and doing Seco etching, you see how dreadful this material is if you want to say what the dominant recombination mechanisms are. You have, in this tiny bit here, you've got clusters of dislocations, you've got grain boundaries with decoration on here, with precipitates on. You've got all sorts of things that are difficult to identify. So if you put a Schottky diode on there, like that, and we can see where it is in the lifetime map. And we started off doing this on 0.5 millimeter Schottky diodes, because this was about the resolution of the lifetime method. But you put a diode 0.5 millimeter, and we can now go down to about 100 microns. But, wrong way. You see, if you do that, even 100 microns, you'll be lucky to get an area that's uniform. You would never get a area that's uniform in this bad bit. In the good bits you can. And this is the sort of thing we get from the good bits with DLTS. But in general, broad peaks, and this is due to the localized strain in the material. And we see this peak, which is generally associated with dislocations. It's easily passivated with hydrogen, and it reduces dramatically with hydrogenation. But as you move from different grains, you go to grain boundaries, there's not a lot of difference in the good bits. So it's been very disappointing, an immense amount of work by me and the students that have worked on that. But we haven't really got very far with cast silicon. Apart from one interesting discovery, and that is precipitation. Precipitates are not really electrically very active. You take a lot of metals, they form a precipitate, it's just the periphery of that precipitate that's electrically active. It's not like it is not like the metal. You're looking, all precipitates are about the same electrically. So we discovered, not actually looking at solar, but by looking at other materials, that in fact very small precipitates behave differently, and they produced very powerful recombination centers. So if you take one of these metals with low diffusivity, so the lighter 3D transition metals or the lighter 4D transition metals, then in the normal process of casting, they produce very, very small precipitates. We're talking of, nanometers. Now, you can see these in, or see something that might be that in synchrotron-based X-ray. So this is some work from Antonio Buonsi when he was one of Ike Weber's students. But in fact, these are most likely inclusions. I don't think they are really precipitates. But this person, Maria Pogliano, working at ST did see things which were quite definitely molybdenum precipitates, not in cast silicon, but in electronic grade. And in fact, rather interestingly, molybdenum is a very common impurity in electronic grade silicon, not from the growth, but in epi, because it transports as the chloride after people have cleaned the tubes. There's volatile chloride around, and so that you see it then in epitaxial material. And this is where we were introduced to this. We had some troubleshooting jobs to do, and in fact, everybody's epi suffers from this from time to time. But also, if you're implanting, 98, which is a common isotope of molybdenum, in the doubly charged state has exactly the same mass as boron fluoride, which of course is used for doping. So you get a mass alias there. So from the stainless steel that's used in semiconductor growth machines and in pipework contains quite a lot of molybdenum, so it transports. So molybdenum is common. And you also see it in cast silicon by SIMS, by mass spectrometry. Now, this is now looking at the epitaxial material in a lattice imaging TM, and you see these defects are very small. You're talking about 2 nanometers across here, and then we can analyze each atom individually in this rather wonderful TM, and these greenish-colored ones are the actual atoms of molybdenum in the silicon matrix. So they definitely exist. We've never been able to see them in cast silicon, but you know it's not easy to see them in anything, things that size, even with the best TMs in the world. So in DLTS, well, this is molybdenum in solution, very well known, very well established, but this is what we see from the nanoprecipitates, and we can characterize that, and it's absolutely remarkable in its recombination activity. It, you know, you measure it, for minority carriers it's greater than 10 to the minus 14, which is enormous, bigger than almost any other transition metal defect that you'll see. But it's also, because of its size, it's also very attractive to majority carriers through a tunneling process. And so that here you have something that doesn't saturate, and that's going to actually kill any material if it's there in high enough concentrations. So this is a very, I mean, something that we're working on at the moment, and very important. And we know it's not. We get electrical confirmation that it's bigger than a normal point defect by the line broadening in the Laplace here. And we see this in good parts of cast silicon. So we believe that it's there in cast silicon. And but difficult to see in the bad regions. You can see the strain in Raman, and it really makes it so difficult to do DLTS, either Laplace or conventional DLTS. So Kerfless silicon, I hope there's nobody coming in here. I'm afraid I've overrun a bit. Kerfless silicon, this crystal solar, again a collaboration with Tony Buonassi. Tony Buonassi discovered that if you anneal this material, and they had funding as a startup in the States to design this rather fancy furnace here, where they could churn out 500 slices an hour grown on porous silicon. It's very high quality material, and they use trichlorosilane to do that, and heating from lamps. And this is the effect that, and the material was no good. And Tony Buonassi discovered that if you went through a particular anneal cycle, then you got 1,000 times improvement in lifetime just by gettering. And so the N-type material was, in those early experiments, was about a millisecond. And this is what you'd expect from the iron that we detected in it. And this is where it sits in terms of the lifetime and the iron concentration. So there is iron there, but it's not the thing that's limiting the lifetime. And so we did DLTS on this, and the results was just amazing. It took an afternoon, and you discovered some very distinct peaks that disappeared totally on the gettering. And then we plotted these, do the Arrhenius plot, and it's platinum. 2 charge states of platinum. This is in the N-type, this is in the P-type. This one doesn't agree exactly, but this is field dependent. So in this material was more highly doped, so the Arrhenius plot was slightly different. So we told, we had a meeting, Tony Buonassi and the company, can't possibly be platinum. This is ridiculous. You know, how would platinum get into solar material? So we then added hydrogen, and we got the platinum hydrogen center. And then, you know, so they went back, and eventually, of course, you realize that it's in making the porous silicon that they're contaminating with platinum, because they're using platinum electrodes. So now they have a process that works without gettering. Well, hydrogen, very aggressive, very reactive material in its atomic form, diffuses rapidly in silicon, expects to be a very effective passivator. It is the passivator in MOS. And there's a lot of problems in understanding how it works. So this is the compilation of all the diffusion data on hydrogen, and this line is an extrapolation of the original data that was done by a very high temperature diffusing. This is looking at atomic motion, and they all agree very well. But you look at what most people get, and it's all over the place, essentially by scattering, by trapping at various impurities. So the hydrogen is so reactive that it doesn't diffuse all that fast in many conditions, because it ties itself on to other defects. So I put on this plot interstitial iron, which is about here, and boron, which is about here, and I did intend to put copper on, but didn't get around to it. And copper is faster, it's about here. So let's look at a 5D metal now, platinum. And we know, in fact, from a lot of experiments that platinum forms first 1 hydrogen, then 2 hydrogen, then 3 hydrogens, and 4 hydrogens it's inert. And we can see this by just etching and looking at the concentration of the various species of platinum. And you get this nice curve, and again they've got very distinct DLTS curves. It doesn't bond very firmly. We got a problem with people, right? Doesn't bond very firmly. The hydrogen here is in the anti-bonding position, and we can determine this from the Laplace DLTS. So I'm afraid I've run out of time. Very sorry about that. But you have the slides, and they will be done later. So I'm sorry that I overran and didn't get the rest of the hydrogenation in. But thank you very much.